physicists. I'm so glad that you're able to join us for one more little lesson on reflection and refraction. This is some of my favorite stuff when it comes to um, light hitting a boundary, and so I'm really glad that you're here to do this. And we'll make it quick, but I do think it'll be worth your time. So let's take a look here. We are going to talk about case three. Case three is like I said, kind of the most interesting, I think. And instead of having a flat boundary, which is what we had in both cases one and case two, we're going to make it a curved boundary now. And when you start talking about curved boundaries, then we get to create these things called images, and it gets to be really, really awesome. So we're going to talk about what that is going to look like in a couple of ways. But we're going to go and write down with that curved boundary what happens. We're going to form an image in a specific place. And that's where it gets kind of interesting. Now, before we go on, I do want to talk a little bit about it in terms of just a flat mirror. We talked earlier during case one about looking in a mirror while you were brushing your teeth and seeing your reflection. We didn't really get into the why of that. So I just wanted to share this with you. So I'm going to draw this as like the mirror in your bathroom, right? So here's your air, and then here's the glass. Okay. And you're standing there, and I'm not an artist. You all know this, but I'm just going to go ahead and draw your face. So there's your head, and here's your eye. Okay. With your little eyelashes, and here's your hair up here, and here's your smile here. And as you're looking into that um, mirror, you are able to see your entire face. So, really, what you're seeing is a person or an image that appears over here with your eye. Oops, I guess I kind of drew that upside down, and your curly hair up here and your smile here. And the reason that that happens is because of the law of reflection. So you remember from case one and case two that light is going to come in and it's going to be incident. I'm going to try to draw this as best as I can. And the light in, the angle in is going to equal the same as the angle out, and that light is going to bounce back and it's going to bounce to your eye. So you're going to have light that comes from your hair. It's going to come in, it's going to hit that boundary, and it's going to look from your eye like it's coming from your hair. It's going to come to your eye. And then there's also going to be another little bit of light that comes from your chin, and it comes in and it hits the mirror. Angle in equals angle out, and that's going to come in just like that. So there's light from your chin that hits your eye as well, and that makes it look like it's coming from there. So this is why you see this thing. So just from our terminology perspective, which is what I wanted to share with you, you in this picture are the object. You're the thing that is being reflected, or when we get to refraction, refracted. And the thing that you see is called the image. That is what your brain sees as this thing. And it's funny because when you're looking at a plain mirror, the image doesn't actually exist. It's not like there's another you on the other side of the mirror. Sorry, spoiler alert if you had that kind of in your brain. Nope, there is not another you behind that mirror. There's just the one, and the light is being reflected. Okay, so you've got your object, and then the image is what your brain sees as that thing that exists over there. Okay, so that's what happens with a flat mirror. The same kind of thing is going to happen with a curved mirror as well. We're going to look at three examples. We're going to go from kind of goofy and silly down to terribly practical. Okay, so the first one that we're going to talk about is the reflection that you might see in a spoon. And for this example, you kind of have to have a shiny spoon. So if you're just using a plastic spoon or something like that, you're not going to quite see this. But if you look in a nice shiny spoon, you can actually see an image of yourself in that spoon. Okay, so worth a try. Maybe go pause the video for a second and go grab a spoon, take a look. Okay, I'm going to show you a video. This is kind of a goofy little video. The it's but it works. So I'm going to go ahead and show it to you, and then we'll talk a little bit about it. Let me see if I can. Oh my goodness, I'm kind of breaking it here. Whoa, let's get back to the beginning, shall we? There we go. Play. So that was kind of opposite of what we saw when we had just the plain mirror, right? So the light from your feet comes up higher, the light from your face goes down low, and that is the inversion that we see. So it's kind of a weird thing if you have a sibling that you like to play tricks on and you have a particularly shiny spoon, you can also kind of mess with them because right in between when you're upside down and when you're right side up, indeed, you actually go away for a split moment, not moment, but a split spot right at the focal length. There is no image. There's a lot of good physics that lives in there, but for our case, we're just going to pay attention to that idea of the spoon and know that the image in it's called a concave mirror can results in it can be either inverted or upright depending on where the object, the person, the thing is relative to where the mirror is. So it's kind of a cool thing. So that curved spoon, that's the first piece here. Now we're going to take that one step further to a fun demo. Again, all these cool demos that we're missing out on, but this video will kind of help you to see it. So this next thing is called a mirage, and it's a nice application of a concave mirror as well. Let's see if I can turn the volume up a little bit here so that you could see it too. Hold on just a second. So you may have seen this thing before. It's a nice little curved mirror game. Here, let me turn my sound up so you can hear it a little bit better. And I'm going to make it a little bit bigger. And this is a quick one, so we'll go back to the beginning here. And this is one of those things that it looks there, and then when you go up and try to grab it, because your friends might just not be very good at grabbing things, you go up to grab it, it legit isn't there. You can't touch it. Okay, so how does this work? Well, it's really just two curved mirrors um, right next to each other. So I have this nice little ray diagram. Again, I don't expect that you can recreate this or anything like that, but I just want to show you this because it's kind of cool. So right down here, this is the first mirror. Okay, and these are just curved mirrors, kind of like a spoon. He said it's parabolic, and if you play with the math, you can get into all these pieces, but we're not going to worry about all that. The little piggy was sitting right here, so here he is. He's standing there, with curly tail and his head and his little snout. There he is. Okay, so there's the pig, and the light from the pig does all of this crazy bouncing. So there's some light that goes up and then down and then up. Ha! And there's some that goes up and then down and then up. And if you notice, all of these things converge right there. So the focal point of that first mirror and the focal point of, well, the location of this mirror are set such that it appears that that little pig that was sitting down at the bottom under on that little bowl, it looks like it's actually sitting right up in that hole. It's so cool. Definitely, if you have a chance, take a look. If you've never seen one before, stop by next year and ask me, and I'll show it to you. It's super neat. So that's the second one, the second little um, example that we're going to do. It's called the Mirage, and it uses two concave mirrors to make an image. And the kind of key that I want to share with you there is that this thing is called a virtual image. So the light rays converge. I'm sorry, it's not actually a virtual image. It is a real image. Sorry about that. It is a real image. Don't quote me on that last thing, or I'll be very embarrassed. But that real image looks like it's there. It looks like you could pick it up. But alas, it's just light that is converging, not actually the. Okay, so those are the two kind of fun examples. The third one is the much more practical one, the one that you have used and you enjoy very often, I would imagine, and that is a satellite dish. So the weird thing here, friends, is that a satellite dish is actually a mirror. You look at it and you can't see your face in the same way that you can in a flat mirror and a spoon. But a satellite dish is a mirror, but it's a mirror for radio waves. If you remember, if you played with us when we were talking about electromagnetic waves, radio waves have really, really big wavelengths. And as a result, even though it looks like it's see-through, you've seen really big um, satellite dishes like this kind before, like I can see through that with my visible light, but with radio waves, because their wavelengths are so big, they actually see, I'm putting in big air quotes there, they see that structure as shiny. And so those radio waves actually bounce off of this curved mirror, just like the visible waves do off of the spoon or off of the mirage, and they bounce back. And they do exactly the same thing we saw before. So the waves come in, and then they bounce back, and they come in and they bounce back, and all of them bounce back to that thing that again is called the focal point, and that's where the receiver is. That's where the receiver is that collects all that data and makes your phone work. It makes your like your satellite TV work. Any of those things all work from that same idea. I also just want to show you this because I think it's so cool. This is the largest radio telescope in the world. It's in Puerto Rico, and it has a diameter of 305 meters. So this is up in the mountains in Puerto Rico. So like you can see up here, this is a mountain here, and this is a mountain. This is like in a big basin, and this huge dish reflects light from the universe, right, from our galaxy and from the universe. So the light comes in, and then it bounces up, and the actual receiver is right there. It's hanging from these towers. So there's cables that go like this, and that's actually it's kind of distorted in this picture. But all of the light, and by light I mean radio waves, collects right there. And oh my gosh, it collects data so that we can see in outer space. Pretty awesome. All right, so those are my three good examples of curved mirrors and what they can do for us. So I'm going to write this down here. We're just going to write down satellite dishes. Okay, they look shiny to radio waves, which is just kind of a cool, crazy thing. Okay, and all of the light reflects to the receiver at the focal point. Okay, now just a couple of minutes to talk about refraction and how refraction works with a curved surface. So simplest example here, oops, not that one, let's do this one first, is a magnifying glass. So a magnifying glass, you use that to look at bugs. You use that to melt crayons. Maybe you use that to read something, or you've seen, like maybe your grandparents use a magnifying glass to read like the newspaper or something like that. So literally what it's doing, it's the same thing. It's following Snell's law. It's doing the exact same thing that we talked about before. My object, so my letters, like if I'm trying to read the newspaper, right? My letters appear to be bigger because the light, as it is traveling from the object to my eye, instead of going straight, it follows Snell's law and it bends. And this light follows Snell's law, and this one actually goes straight. And then we can do all of the pieces, and we actually get to make this image over here that appears bigger. Okay, so that's kind of cool. I'm just going to keep cruising because lenses in magnifying glasses are cool, but we all have some pretty solid lenses right in front of us in our eyes. So the eye does exactly the same thing. So the lens in your eye is actually pretty amazing. Um, it adjusts if you're looking like nearby or far away, and it adjusts so that you can see what you're looking at. So from very far away, you've got your lens. This is the lens right here, right? And it is able to focus an image back on your retina so that you can actually see. Okay. If you're looking at something close, you can see that the lens changes shape so that it changes the focal point or the focal length so that you can see this. I guess that's like a button or something like that. Okay, so fun fact, right here where your optical nerve comes in, there is actually a blind spot, so you can't actually see things at a very specific place um, based on where it is, where the light is when it comes in through the lens in your eye. So that's kind of cool. Um, Eyes are amazing. I'm not a biologist, but holy cow, I think that they're pretty awesome things. Some of you have lenses in your eyes that need a little bit of assistance, right? So there are three common vision. Everything that I found said defects. That sounds like you're broken, and I don't think that you are, but just three common vision challenges, we'll say. So one of them is farsightedness. Farsightedness means that you are not able, like the lens of your eye is not able to focus on things um, that are close by, right? So it tries to make that image way far back here, right? Nearsightedness is exactly the opposite. It tries to make the image right there. And in doing so, astigmatism does kind of a cool thing too, but I'm not going to get into that right now. These are the ones that I want to focus on, the farsightedness and nearsightedness, because they're a little simpler. By putting a second lens in front of your eye, it allows that light to be bent twice. So it gets bent first through the lens, either the contact lens right against the lens of your eye or the lens in your glasses, and it bends the light once and then a second time here, so that instead of focusing the light way back here where the image can't be seen or would be blurry to you, it focuses it right on the retina, which is where you want it to be, which is pretty awesome. Same thing here. We have lens number one, okay, for nearsightedness, and then lens number two, your eye, and that allows for the image to form where your eye can see it and where your brain can process it. So there you go. That is what I'm talking about for case number 3. This is all about lenses, magnifying glass, your eye. So cool, so cool. And then we'll say glasses or contacts to assist um, your eye to form the image. That's it, you guys. Thanks for watching. Have an awesome, awesome day. As always, if you have questions, reach out. Maybe we'll talk on Monday or any other time. Be well, stay safe, take care.